Now that we've been using degrees of freedom for a couple months, I'm going to take a stab at explaining what they mean. So if you look at the textbook definitions of degrees of freedom, you might get something like this first one. Degrees of freedom are the number of independent values that a statistical analysis can estimate. Still as clear as mud. We could look at the second one. I think this one's a little more helpful. You can think of it as the number of values in a sample that are free to vary as you estimate a parameter. Now remember, parameter is something we try to estimate about a population, like the population mean, or the population standard deviation, or the population proportion. And we estimate those using samples because normally we can't really know what they are in the population. So let's just look at an example. Let's say we collect a random sample of size 10 to estimate a mean. Alright, in context, maybe we want to estimate the weight in kilograms of the average bunny rabbit. So we're estimating the weight of the Easter bunny. So we go out and we find 10 potential Easter bunnies to weigh, and we're going to use those to estimate the mean weight of all Easter bunnies. Each observation in our sample is independent, so the weight of Easter bunny number 1 is independent of the weight of Easter bunny number 2, which is independent of the weight of Easter bunny number 3, and so on and so forth. Which should happen when you have a random sample. After we collect our sample, we find that the mean weight is 7 kilograms for an Easter bunny. So what might our sample look like? Well, we're going to add 10 numbers together. So a number plus a number plus another bunny rabbit, plus another bunny rabbit, plus another bunny rabbit, plus another bunny rabbit. How many is that? 6. Plus another bunny, plus another bunny, plus another bunny, plus another bunny. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 equals, scoot that over, equals, well, okay, if we're going to estimate the mean, we'd have to take that sum and divide it by a sample size of 10 to get the mean. So we're going to estimate a mean of 7 kilograms. Okay. Now we're not working backwards. I know we don't normally start out knowing the estimate of 7 before we know the sample, but that's not the point of this. The point is to think about these 10 independent values and what kind of freedom they have to vary in order to produce this sample estimate of the mean. So bunny rabbit number 1, how much could bunny rabbit number 1 weigh? Well, there's all kinds of things it could weigh. It could weigh 10 pounds, or kilograms, it could weigh 5 kilograms, it could weigh 2 kilograms, it could weigh 15 kilograms. Really, it could weigh anything under 70. But that's kind of dumb, because if it weighs 70 and all the others weigh 0, we'll get a mean of 7. So maybe it doesn't weigh a whole lot. Let's just say that the first bunny rabbit weighs 8 kilograms. Now that bunny rabbit's weight is free to vary. It could be lots of different things. It could be any number as long as it doesn't produce a sum bigger than 70. So that one is free to vary. The second bunny rabbit, how much might it weigh? Well, this one's free to vary. It can be lots of different things. It could weigh 1 kilogram, it could weigh 10 kilograms, it could weigh 7 kilograms. Let's say, just for funsies, that it weighed 6 kilograms. It was free to vary. It could have been lots of different things. Third bunny rabbit, it could have lots of different weights. It could weigh 5 kilograms. It could weigh lots of different things. I'm just going to, pretend we picked a bunny rabbit and it was 5. The fourth bunny rabbit could have lots of different weights. It's free to vary. So let's say that one also weighs 8 kilograms. Bunny rabbit number 5. Its weight can be lots of different things. Its weight is free to vary. So let's say that it's an extra fat Easter bunny, so it weighs 10 kilograms. Then we get to bunny rabbit number 6. Bunny rabbit number 6 can still be lots of different weights. It could be 4 kilograms, it could be 2 kilograms, it could be 12 kilograms. Anything that doesn't shove this whole total up to 70 is fine. So let's say that this one is a smaller bunny rabbit and it only weighs 5. Seventh bunny rabbit, it could weigh lots of different things. Its weight is free to vary. So maybe it weighs 7. Bunny rabbit number 8, its weight is free to vary. It can be lots of different numbers. So maybe it weighs 6 kilograms. Bunny rabbit number 9, it can weigh lots of different things. Now, it probably has, at this point in time, before we know what these do, this one has a little less room to vary, but it's still free to vary. It can be what it wants to be, as long as it doesn't shove this total all the way up to 70. So let's say, just for fun, that this one is a pretty big bunny rabbit as well, so it weighs 9 kilograms. Now, once those 9 are in place, is this one free to vary? No, because all of a sudden these sum up to 64, and there's only one weight that this one could be. It has to be 6 to produce a mean of 7. So this one is not free to vary. So one of the bunny rabbit's weights is not free to vary. 9 of them had freedom to vary. 1 does not. So the number of bunny rabbits, or the number of items in our sample size, minus 1 is free to vary. Is free to vary, which means 10 minus 1, or 9, is how many variables are free to vary. So our degrees of freedom for this sample is 9. Okay, it's just the big idea of how many independent values have the freedom to vary if you're estimating a sample parameter, or estimating a population parameter. Sorry. So only one is free to vary. It doesn't matter which one is free. If we knew this bunny rabbit first, and this is the last one we find out, this one's not free to vary, but always one of them in a list like this is free to vary. Okay, now let's look at one other example of degrees of freedom. This time let's look at a chi-square situation. So let's take a two-way table like this one. We want to know if there's an association between eye color and which hand is the dominant hand. So we selected a random sample of independent observations of 100 people. So 100 people we found out whether they were left or right-handed and what color their eyes were. Some were blue, some were brown, some were green, some didn't classify themselves as any of those. I'm not sure what other is, but it's something other than the other 3. How many of the observations here are free to vary if we know the totals? So totals are parameters. So let's see what's free to vary. Can the number of left-handed brown-eyed people vary? Sure. As long as that number is less than 40 and less than 20, it's free to vary. So we could have potentially 10 left-handed people. I'm going to pick easy numbers. 10 left-handed people who have brown eyes. We could sample that many. Is that number free to vary? Sure. That number is free to vary. It could be anything. I'm going to circle it because it's free to vary. Is the number of right-handed people with brown eyes free to vary? Nope, it can't be, because 10 plus the right-handers has to equal 40. Right-handers has to be 30. It's not free to vary. So this one has no freedom of variation. Okay, let's just pick another spot. Let's go with green eyes right here. Let's say that we had some number of green-eyed right-handed people. Now that number has to be smaller than 80 and smaller than 20. So let's say that we had 10 people, because I like easy numbers, 10 people who were green-eyed right-handed people in our sample. That was free to vary. It could have been a 10, it could have been an 8, could have been a 15, could have been a 19, could have been a 3. That's free to vary. Is the left-handed people with green eyes free to vary? Nope. Nope. It has to be 10, because 10 plus 10 is 20. That one was not free to vary. It had to be 10. It didn't have a choice. Alright, if we pick another spot, let's see. Left-handed people with other color eyes. Let's say we had 2 people with left-handed and other colors. Is that number free to vary? Sure, it could have been 5, it could have been 7, it could have been 12, it could have been anything less than 20 or less than 15, well, less than or equal to. If that one is 2, is this one free to vary? Nope, absolutely not, because 2 plus what is 15? Well, this has to be 13. It can't vary. It is what it is. it has no freedom of variation. Alright, is this number free to vary? Nope, can't be, because the left-handers have to add up to 20. So if we have 10 plus 2 plus, I goofed. Did you notice that I goofed? I totally goofed on that. I needed a different pair of numbers there. I have too many left-handers. Oh no. Okay, which means I have to fix my numbers. Oh my. Let's see. Let's say here we had, I'm going to change it to 15 people in this one. That was free to vary. And 5 people here. I get to do that because I'm the teacher. Now we have 10, 15, 17 people who are left-handed. Okay, that makes some sense. What I had before did not make sense because I was making up numbers just out of the deep blue sky. This one didn't have freedom to vary if 15 was set in stone, if it was known. But in the left-hand column, we know things have to add up to 20, which means the blue-eyed left-handed people do not have any freedom to vary. They have to be 3 because 10 plus 3 plus 5 plus 2 have to add up to 20. So 3 was not free to vary. And in the right-handed column, the right-handed blue-eyed people, they don't have any freedom to vary either because, oh, please let this work. 30 plus 15 is 45 plus 13 is 58. This is 22, but that didn't have any freedom to vary. 22 plus 3 is 25. 22 adds, so that one wasn't free to vary. So that means we have total 1, 2, 3 degrees of freedom, because only 3 observations were free to vary in this situation. Now the formula we use is number of rows minus 1 times number of columns minus 1. And that comes into play because once you know everything except for one thing in a row and everything except for one thing in a column, you know everything there is to know. And I probably didn't say that quite right, but you can pretend it was beautiful. In rows, we have 4 rows minus 1. We have 2 columns minus 1. That's 3 times 1, which is 3. And that's the number of degrees of freedom. That's how many numbers in that table were free to vary. So there you go. Degrees of freedom in a nutshell. If it's still clear as mud, okay, just learn your formulas and keep on trucking.